All right, pilot, welcome aboard the Aegis. You're in the command chair of a top-of-the-line research sub, and your deep-sea mission is officially a go. Today, we're doing more than just exploring. We're going to master the math that keeps this sub in one piece in the crushing dark. Let's do this.
Okay, all systems are green and you have the con. As we start our descent, remember that every single calculation you make from here on out is absolutely critical. And guess what? Your first challenge is already popping up on the console.
And here we go. First alert. The hull is taking a beating, not just from the pressure, but from a wild temperature swing. You get this calculation wrong, and we are in big trouble. Your job is to figure out the exact thermal stress on the Aegis.
So, check this out. Inside the cockpit with us, it's a pretty comfortable 26.1 degrees Celsius. But just on the other side of this hull, the water is a bone-chilling negative 12.6 degrees. That is a massive difference. So, what's the actual gap between inside and out? The equation looks simple enough, right? 26.1 minus negative 12.6. But be careful, those two negative signs sitting next to each other, that's a classic trap that can sink a mission fast. Here's the key to solving this, and you gotta remember it, adding the opposite. When you subtract a negative number, you're not really taking anything away. Think of it like you're canceling a debt, which actually makes you richer. You're increasing the total value. So our whole problem just transforms. That 26.1 minus negative 12.6 actually becomes 26.1 plus 12.6, which means the total temperature difference is a whopping 38.7 degrees. Whoa! Okay, systems are stable. Nice work, pilot. All right, a quick cockpit check. One of the most common rookie mistakes is messing up the keys on the calculator. You've got a button to make a number negative, and you've got a button to subtract. They are not the same thing. One tells you the value of a number, the other is an action. If you mix them up, your navigational computer is going to go haywire. Now, what happens when you're adding a negative? The best way to think about this is like a game of tug-of-war. You've got the positive side pulling with a force of 2.65, and you've got the negative side pulling with a force of 3.81. Just by looking at the numbers, who do you think is stronger? Yep, the negative number is stronger here. It's got more muscle, so it yanks the final answer over to its side of the zero line. The result is negative 1.16. It's a really simple way to picture which way the answer is going to go. Okay, the hull is secure. That's good news. Let's get to the next challenge. Now, we got to keep an eye on our power reserves. You know, the very thing keeping the lights on and the air flowing down here. And, speak of the devil, there's the alert. We've got a steady power drain. For every single hour we're down in the deep, our batteries lose 2.6 units of power. That's a constant negative we have to deal with. So Mission Control says we have another 3.5 hours down here. Your job is to tell me exactly how much power we're going to lose in that time. This one's a multiplication problem, and the signs are everything. For any multiplying or dividing you do, you have to live by the golden rule of signs. It's really simple. If the signs are the same, so two positives or two negatives, your answer is always positive. If the signs are different, one positive, one negative, your answer is always negative. That's it. That's the whole rule. So let's use the rule right now. Our time, 3.5 hours, is a positive number. Our power drain, 2.6 units, is a negative. So we're multiplying a positive by a negative. The signs are different, so the answer has to be negative. Total power loss, 9.1 units. And by the way, this rule works exactly the same for division. No tricks. If you ever need to divide a negative number by another negative number, the two negatives just cancel each other out, and you end up with a positive answer. Sometimes two wrongs really do make a right. All right, pilot, you're doing great. Now for the final challenge. This one puts everything we've talked about together. The Aegis needs to perform a few maneuvers, and we have to calculate our net depth change. No pressure, but if you get this wrong, we could be miles off course. Okay, here's the plan. For the first 10 seconds, we're going to rise up at 0.8 meters per second. Right after that, for the next 6 seconds, we're going to dive at 0.6 meters per second. So we're going up a bit, then down a bit. And this is what that looks like as one big math problem. You've got multiplication, you've got addition, you've got positive and negative decimals. And let me be clear, you cannot just solve this from left to right. There's a strict protocol you have to follow. And that protocol is called BEDMAS. This is the non-negotiable order of operations. You do what's in the brackets first, then you handle any exponents, then you do all the division and multiplication, and only at the very end do you do the addition and subtraction. It's the only way to make sure everyone gets the same right answer. So let's follow the protocol. First, the brackets. 10 times 0.8 is 8. 6 times negative 0.6 is negative 3.6. Okay, now that the multiplication is done, we can do the addition. 8 plus negative 3.6 gives us 4.4 meters. So after all that, we actually ended up higher than we started, a net ascent of 4.4 meters. Perfect.
So why is this BEDMAS thing such a big deal? Well, we ran this exact problem in the simulator with two trainees, Leslie and Zach. Leslie followed the protocol. She got the right answer. Zach just went left to right, and his answer was way off, dangerously off. So the lesson here is simple. Don't be a Zach. Always follow the protocol.
And you nailed it. Every calculation, flawless. The mission is a success. We are heading back to the surface. Let's quickly go over what we learned down there.
Here's what it all boils down to. These decimals, these signs, they're not just numbers in a textbook. They are the coordinates that guide you through complex problems. So just remember this, master the signs, follow the order, and you'll never be lost.
And that brings us to one last thought for the day. As an engineer, what do you think is the tougher challenge? Designing a submarine to handle the crushing positive pressure of the deep ocean, pushing in on it from every side, or designing a spacecraft to handle the extreme negative pressure of a vacuum pulling out on it? Which is harder and why? Let me know what you think. Stay sharp, and I'll see you on the next mission.